The name of this video is Work on Conductor. In fact, we are going to generalize the concept of work on circuit, which was intended to be a filiform or quasi-filiform circuit, to a bulk conductor. So bulk is the key idea here. And let's say that the gain is a rigid bulk conductor for simplicity. Could be flexible as well, but let's say it's rigid for simplicity. So let's make a sketch of a conductor. It can be still a circuit, okay? But instead of being a wire, it has finite dimensions in every direction. And let's take a part of that bulk wire, so a big thick wire. And so, for example, we would have, this is one side here, and it continues like that, something like this. So now, every time we consider a bulk capital omega wire as such, so this is a bulk circuit. So just to recap, okay? So I know there is always some confusion with circuit, wire, conductor. So a circuit is something which typically, closes around in a sort of a loop, and it's used in circuit theory. And it can be filiform or quasi-filiform, and then we call it a wire, or it can be bulk, like a real bulk conductor, like the one we are considering in this case. They are both circuits if you want, okay? You just need to be specific and reiterate over and over what you mean. If you mean like a quasi-filiform or filiform circuit, therefore a wire or a bulk conductor circuit, like this one here, where the dimensions are not negligible in any direction. Okay, so every time we have at hand a problem with a bulk conductor, in the case of currents, we need to pause and think about it. We need to split it into an infinite set of filiform flux tubes, the usual spaghetti, which we used to do already in 242. So this is one of the spaghetto, this is another one, this is another one, it goes like that, and so on and so forth. So we make an infinite set of these spaghetti, which are, technically speaking, filiform flux tubes. Therefore, if the overall current carried by this cross-sectional area here, current intensity is I and is a steady current, as always. What is the current carried by each of these circuits? Well, of course, there will be a current I1 dot a current I small n dot a current I capital N, where n eventually is a very large number. In principle, if you really want to do it formally, it should be an infinite set. Now I'm just doing a sum over a finite but large set of filiform flux tubes, something we've done already in 242. So for now, we can use the same result for the work which we found in the case of filiform circuits, okay, of wires, and we can apply that result for each flux tube and then sum it up for all the flux tubes. Again, you should do the integral in the case of an infinite set of these flux tubes. Now I'm just doing the sum over them. So it could also be quasi-filiform, it doesn't really matter. I mean, the concept, I believe it's clear of the procedure I'm following here. So the work W1 associated with the first wire, which is one of these filiform or quasi-filiform flux tubes, okay, should be again an infinite set, but I just consider a very large number for simplicity, is going to be the current carried by that wire times the flux difference between the flux linked with that wire at the final configuration minus the flux linked with that wire 1 at the initial configuration. Okay, because I'm displacing this conductor, lives in an external field B naught. So this is my external magnetostatic field B naught, and I'm displacing it by a certain amount. Let's say we can call it small r, some quantity. So we are displacing it by some amount in presence of an external field B naught. It's rigid, so we only care about the external field. This is the work W1. Dot, so the work on the nth, small nth generic circuit is going to be In, the current that1, phi n final, small n, the intermediate step, times phi n initial. And finally, on the last, which again, if I were to integrate over this filiform of quasi-filiform flux tubes, I should go to infinite. And in this case, I just call it I capital N, is just a large number, phi n capital N final minus phi capital N initial. Great, these are all the works. What is the overall work to move the entire circuit? As I said, either I integrate if I consider an infinite set. I'm not considering infinite set for simplicity, so I need to sum it up, and so the total work W on the entire circuit is going to be the sum for small n, which goes from 1 to capital N, of W small n. So let's sum it up in this fashion. So we have two series here. One series, the positive one, and the other one is negative. So positive, let's do it orange. And so we're going to have I1, positive I1, times phi 1 final. This is the one which I need to subtract. This is the plus one, and the initial one is the one I need to subtract from this. So let's begin with all these final ones. So plus dot plus I small n phi small n final plus dot plus I capital N phi capital N final. This, I need to subtract from this the other contribution, which is minus I1 phi 1 initial, and let's put this in parentheses. So here I put the plus, but remember that it's a minus. A plus I small n. These are all the flux linked with each of these tubes in the initial configuration. Initial. And remember again, there is a minus sign in front of all this series. Now, the top series, we can redefine it simply as an overall current I. By definition, there is nothing surprising, just my definition. This series, I call it I times phi final. And again, it's my definition. I can do whatever, I can call it whatever I want. Whereas the bottom one, I call it I times phi initial. And of course, you need to remember that this is the minus sign. Under these conditions, this overall work can be finally rewritten as the current I defined by these two definitions up here times delta phi, to be intended as phi final minus phi initial. So this is the result for the work which we wanted to find, which is the generalization of the one we found before to the case of a bulk conductor. Now, incidentally, it so happens that these definitions generalize the concept of inductance, self and mutual inductance for non-filiform or quasi-filiform conductors, that is for bulk conductors. In fact, for example, you could, from the definition I phi final equal I1 phi 1 final plus, let me go straight to the last one, which is to the generic one, I small n phi small n final, and the same thing applies to the initial one. You can rewrite this quantity as the flux phi final, or any flux. Let's consider the final flux here. We can rewrite it as I1 divided by I times phi 1 final plus dot plus In divided by I. So that kind of definition allows us to redefine the concept of inductance or mutual inductance, self or mutual inductance for bulk conductors, if you want. We will not use it too much. I just want to give a sort of a hint. We don't have to. You can discuss in Piazza if you want about it. It's not super critical, but that's the in essence. This is the generalization which allows you to define LNM for bulk conductors. Instead, what I want to touch up here a little bit is that if I make a displacement, actually let's call it dr for simplicity, of this rigid circuit in some direction, Okay, so if I make such a displacement, what is I want to find the overall net force, F net, let's call it the overall magnetic force acting on this object. So what is the mathematical procedure to do that? Well, we know that dW is equal to the total net force, which is going to be, let's just call it F net, dotted with dr. This has to be equal to, by our definition from our previous calculation, I d phi. So for example, in a Cartesian coordinate system, if this dr, we write it as dx ux, for example, just to fix ideas, well then in this case, we will find that this F net along the x direction, basically, this quantity here times dx has to be equal, because that's what I'm doing here. I'm dotting with ux, obviously it's just the x component has to be equal to I d phi. And so to generalize, we could write in a Cartesian coordinate system all these net forces, like x component is going to be the partial derivative with respect to x of the flux times the current I, and similarly for the similar for y and z, which I'm not going to do. The other thing you can also do is to find the total torque on this system, on this conductor. And so how do you do that? Well, let me sketch in 2D if I want to do the torque. So this is for the total net force and the total torque. Okay, so this is for F net. Now what about gamma net, which is again the torque? Okay, so in the case of the torque, let me sketch a two-dimensional Cartesian coordinate system. You can generalize simply to 3D, but for simplicity, let me do it in 2D. So this would be x, this would be y, this is the origin, and let me now translate it by a certain amount, so that this is x prime, and this one is y prime, such that this angle here is alpha, and this angle here is beta. These are the angles. So x goes to x prime by an angle alpha, and beta is the angle which goes from y to y prime, and I can make it general as much as I can generalize this to any angle you want. And so in this case, the net, the gamma x, net x, the net torque, is going to be similar to this definition here. It's going to be the current, but now I have the partial derivative with respect to that angle, which I can vary, of the flux. And of course, I can do the same thing for beta and a gamma if I go to 3D. And so this is the way you get the torque, okay? So to summarize this video, the key idea here is we want to consider a bulk rigid conductor. We split it in an infinite or a very large set of filiform or quasi-filiform flux tubes, the usual procedure. If the total current is I steady, each of these currents is I1, I2, IN. If I sum them up, I get this I steady here, okay? So that's what I get by summing them up. And so the work, I can use the definition for each filiform flux tube, the same we have done for filiform wires. So it's the current on that tube, for example, the nth one, times the n flux linked with that tube at the final configuration minus the initial configuration. I sum it up. Of course, it could be an integral if I went to infinite, an infinite set of tubes. And so then I make these new two definitions, and again, I know that people here do mistakes, it's just a definition, which allows us simply to rewrite the work in this fashion, which again, similar to the one we found before, but now we generalize to the case of bar conductors. And I also briefly touch on the net force and the net torque, which, how to calculate them, for example, in a Cartesian coordinate system, or given some angles, some rotational angles here. Also, I think it's worth reminding here ourselves that these angles, alpha and beta, of course, they are intended to be as variables, okay? So, of course, alpha can be the same as beta in here as a number, but actually these are variables. That's why we are deriving with respect to alpha and beta again as variables. In addition, another interesting point which is worth pointing out up here is that the reason why dW is infinitesimally small is because I'm translating the whole bulk conductor by dr, and it's not because the net force is infinitesimal. This is the net force on the entire conductor, so it's finite, but the translation is infinitesimally small. And that's it.